Pluto, a remote and cryptic divine substance, was previously perceived as an unmistakable and substantial planet inside our planetary group. It was viewed as a component of the planetary family until later provocative declarations by prominent astrophysicists Neil deGrasse Tyson and Michio Kaku brought Pluto back into focus. These distinguished experts have made a stunning statement: Pluto could be on a potential collision course with Neptune. But how could such an event even happen? What might be the consequences of such a massive event? Are we witnessing a remarkable cosmic peculiarity? Or is there more to this approaching celestial event than what initially seems apparent? Join us as we examine the potential consequences of a possible Pluto-Neptune impact. Pluto, once classified as a planet but later redefined as a dwarf planet, continues to intrigue and captivate the interest of astronomers and scientists within the vast universe. Studies by top space scientists suggest Pluto's orbit lies dangerously close to Neptune's. Prominent astrophysicists such as Tyson and Kaku have voiced concerns over the possible risks of a collision between these two celestial bodies, which could pose a significant threat to Earth. But how could such a catastrophic scenario unfold? Pluto's orbit around the Sun is distinct from that of any other planet in the solar system. Takes an astonishing 248 years to complete a single orbit. This means that since its discovery in 1930, Pluto has not yet completed even one full revolution around the Sun. However, the intrigue does not end there. Pluto's orbit is characterized by an unusual shape, vastly different from the nearly circular orbits of the major planets. What makes Pluto's path even more unpredictable is its 17 degrees inclination relative to the ecliptic plane, making its orbit far more irregular compared to other planets. This anomaly introduces additional complexity to Pluto's orbital dynamics. One of the most fascinating aspects of Pluto's orbit is its interaction with Neptune. For approximately 20 years in each orbit, Pluto actually crosses inside Neptune's path around the Sun, defying expectations based on their respective positions within the solar system. This raises an obvious question: why hasn't Pluto crashed into Neptune yet? The answer lies in the gravitational interactions of other planets within the system. The study of Pluto's orbit began soon after its discovery. Initially, astronomers were puzzled by its erratic trajectory. Unlike other planets whose orbits are closely aligned with the ecliptic plane, Pluto's orbital path stood out due to its steep inclination and eccentric shape. The mystery surrounding Pluto's orbital behavior can be explained by a concept called the three-body problem in celestial mechanics, which seeks to understand the movements and interactions of three objects, Pluto, Neptune, and the Sun, under their mutual gravitational forces. It involves predicting the future positions of these bodies based on their current positions and how they influence each other. For Pluto, this issue demonstrates that the orbits of Pluto, Neptune, and the Sun interact in a complex manner. Key terms like asymmetric libration, scope libration, and VSK wobbling are crucial to solving this puzzle. Astrophysicists speculate that the reason all planets maintain their orbits is due to a phenomenon known as libration. In Pluto and Neptune's case, when Pluto crosses Neptune's orbit, their relative positions are offset by about 90 degrees. This separation is crucial in preventing their orbits from overlapping and resulting in a collision. Additionally, libration refers to the vertical oscillation of a celestial body within its orbit. For Pluto, this means that whenever it comes closest to Neptune or another massive planet, it is positioned significantly above the plane of their orbits, further safeguarding it from potential crashes. Another critical factor in this equation is the VSK wobbling, named after the researchers who first explored how objects move in space. The VSK wobbling describes how the gravitational forces exerted by Pluto, Neptune, and the Sun influence each other's motion. This intricate dance of gravitational interactions maintains Pluto's orbit, even when it follows an eccentric path near the Sun. The VSK wobbling is essential in ensuring Pluto's orbit remains stable for incredibly long periods. Despite the apparent randomness of the system, this phenomenon guarantees that, regardless of Pluto's seemingly chaotic orbit, certain forces and patterns help keep everything in balance. These gravitational forces and anomalies play a crucial role in stabilizing Pluto's orbit, thus preventing potential collisions with Neptune or any other celestial object. The three-body problem is key to understanding how objects in space interact with one another. It provides insights into Pluto's motion and helps astronomers understand the gravitational effects on other distant celestial bodies, including stars and planets. Numerical simulations from the late 1980s demonstrated that, despite Pluto's eccentric orbital features, its trajectory remained stable, with only slight variations from its initial conditions. These characteristics of Pluto's orbit have remained consistent over extended periods, allowing astronomers to refine their understanding. Later computational models also provided clarity on how larger planets, such as Neptune, Jupiter, and Saturn, influence Pluto's orbit. Neptune shares an unusual relationship with Pluto through a 2:3 orbital resonance. Every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance stabilizes Pluto's orbit. However, Neptune's gravitational influence is not the only factor at play. Jupiter's immense gravitational pull also plays a significant role in keeping Pluto's orbit stable. Saturn's gravity further contributes to the stability of the outer reaches of the solar system. Studies suggest that Jupiter's massive gravity is sufficient to ensure Pluto's trajectory remains consistent for exceptionally long periods, potentially even billions of years. Together, Neptune, Jupiter, and Saturn may be working in unison to keep Pluto's path on track, preventing disruptions to its orbit. These irregularities in the planetary system are crucial in maintaining stability within the solar system. Without these forces, the universe could be far more chaotic, with objects like Pluto potentially colliding with other bodies or being ejected from their orbits, causing disturbances among other celestial objects. Understanding Pluto's orbit is particularly crucial, especially as there are theories about a possible collision with Neptune in the distant future. The intricate relationship between Pluto's orbital pattern and Neptune's provides deeper insight into how neighboring planetary systems function and interact. Pluto's case demonstrates that even in seemingly chaotic orbits, equilibrium can be achieved through the intricate interplay of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and analysis to maintain our place in the universe. Studying space often forces us to confront the bizarre and unpredictable nature of celestial bodies. Pluto's orbit serves as a prime example of this unpredictability. The potential for orbital resonance, the fundamental connection between Pluto's and Neptune's orbits, is a key element of this dynamic. The 2:3 orbital resonance ratio between Pluto and Neptune ensures that, despite their intersecting paths, they never collide. This resonance is a fundamental aspect of planetary motion and plays a crucial role in the overall balance of the solar system. The divine riddle forestalling any lamentable cooperations, the reverberation in which Pluto's orbit follows a 2:3 ratio with Neptune's, is a key principle in celestial mechanics. For every 2 orbits Pluto completes, Neptune completes 3. This gravitational resonance stabilizes their orbits, ensuring that, despite their paths crossing, they do not collide. This delicate balance is a remarkable example of how seemingly chaotic systems in space can self-regulate through subtle gravitational forces. Despite Neptune's influence, other massive planets like Jupiter, Saturn, and even Uranus play a role in maintaining balance within the solar system. Jupiter's immense gravitational pull acts as a shield for smaller bodies like Pluto, influencing their orbits and preventing them from deviating off course. Some researchers suggest that Jupiter's gravitational force may have even prevented Pluto from being ejected from the solar system altogether. These findings highlight the importance of understanding the gravitational forces at play within our solar system. While Pluto's orbit remains stable for now, changes could still occur in the future. As astrophysicists like Neil deGrasse Tyson continue to explore the universe, they provide a deeper understanding of the delicate balance that governs the movements of celestial bodies. The possibility of a Pluto-Neptune collision, although unlikely, reminds us of the ever-evolving and intricate nature of the universe, emphasizing the need for ongoing exploration and examination of the forces shaping our solar system. The continued study of Pluto's orbit and its interactions with other celestial bodies is not only crucial for understanding our solar system but also for exploring the broader universe. As scientists like Neil deGrasse Tyson continue to study space dynamics, they emphasize the evolving nature of celestial mechanics and the challenges of predicting the future movements of planets and other celestial objects. The potential for a Pluto-Neptune collision, however improbable, serves as a reminder that the universe is full of uncertainties and that even the most stable systems can undergo significant changes over time. Furthermore, Pluto's situation exemplifies the complexities of orbital resonance, where the movements of celestial bodies are intricately interconnected. The 2:3 orbital resonance between Pluto and Neptune ensures that, despite their intersecting paths, a collision is avoided. This resonance is a direct result of gravitational interactions between the two bodies, establishing a delicate equilibrium that has preserved Pluto's orbit for billions of years. It serves as a perfect example of how gravitational forces in seemingly chaotic systems can produce stable and predictable outcomes over long periods. The significance of this resonance cannot be overstated. It is a fundamental principle in celestial mechanics, demonstrating that even the most irregular and complex orbital patterns can maintain harmony through subtle gravitational influences. This understanding of resonance also extends to the broader dynamics of the solar system, where the interactions between planets, dwarf planets, and other objects are crucial in maintaining stability within the system. Jupiter, in particular, plays a vital role in the overall stability of the solar system. Its massive gravitational influence acts as a protector for smaller bodies like Pluto, preventing them from being ejected or colliding with other objects. Jupiter's gravitational influence extends far beyond Pluto, affecting the orbits of asteroids, comets, and other small bodies in the outer solar system. This further demonstrates the interconnectedness of various objects in the solar system, and how their gravitational forces work together to maintain balance and order. Some experts even suggest that Jupiter's gravitational pull may have played a role in securing Pluto's position in its orbit, preventing it from being expelled from the solar system. This scenario underscores the importance of understanding the role each planet plays in shaping the overall structure and dynamics of the solar system. The study of Pluto's orbit and its interactions with other planets also highlights the fluid nature of space. While mathematical models and virtual simulations provide valuable insights into the behavior of celestial bodies, they also reveal the inherent uncertainties in predicting long-term movements. Minor changes in initial conditions or slight deviations in gravitational forces can lead to vastly different outcomes over time. This uncertainty serves as a reminder of the complexity and unpredictability of space, emphasizing the need for continuous observation and analysis to refine our understanding of the forces that govern the universe. In the broader context of space exploration, Pluto's orbit offers essential lessons about the balance of forces that determine the behavior of celestial bodies. The fact that Pluto's orbit has remained stable for billions of years, despite its unusual characteristics, speaks volumes about the power of gravitational forces and the self-regulating nature of orbital mechanics. This case highlights not only the critical importance of ongoing research but also the need to continually improve our models of how planets and other celestial objects move through space. The ongoing study of Pluto's orbit and its relationship with other celestial objects provides invaluable lessons about the intricate balance of forces that govern movement in space. As space exploration continues to advance, it becomes clear that understanding the delicate interplay of gravitational forces and orbital mechanics is crucial, not only for understanding Pluto's trajectory but also for uncovering the broader dynamics that govern the solar system and the entire universe. By studying systems like Pluto's, scientists gain a deeper understanding of the forces at work in the universe, allowing them to better predict the behavior of other objects in space. Despite Pluto's orbit being stable for billions of years, the complexity of its motion and interactions with other celestial bodies continues to intrigue the scientific community. This unpredictability in the movement of celestial bodies is a key reminder of how dynamic space truly is. The possibility that Pluto's path could change in the distant future, whether due to external forces or shifts in the gravitational influences of nearby objects, serves as a valuable case study for understanding cosmic stability and instability. Even with its current stable trajectory, Pluto's orbit serves as a reminder that our understanding of space must constantly adapt to new discoveries and evolving data. The fact that Pluto has remained in orbit around the Sun without significant alterations or disruptions, despite the seemingly chaotic nature of its path, underscores the resilience and stability of celestial mechanics. Even when its orbit crosses Neptune's, the gravitational resonance between the two bodies prevents any catastrophic scenario from occurring. This stability is an ongoing testament to the power of gravitational interactions in keeping celestial bodies on course for extended periods. What is equally fascinating is the role that other celestial bodies, especially Jupiter, play in maintaining Pluto's orbit. Jupiter's massive gravitational field exerts a far-reaching influence that stabilizes the orbits of smaller bodies like Pluto. This influence also extends to other objects in the outer solar system. In fact, some researchers speculate that Jupiter's. This highlights the importance of understanding not just individual objects but also the broader forces at play within our solar system. The stability of the entire solar system is intricately linked to the interactions between these massive planets, dwarf planets, and other smaller objects. The gravitational resonance between Pluto and Neptune, specifically, their 2:3 orbital relationship, is a prime example of how cosmic interactions can result in long-term stability. This resonance ensures that Pluto and Neptune, despite their intersecting orbits, will never collide. This is because the gravitational forces at play keep the two bodies at a safe distance, allowing their orbits to stabilize each other. Such resonance is not limited to Pluto and Neptune but occurs throughout the solar system. For instance, similar orbital resonances help maintain stability in other planetary orbits, ensuring that the solar system remains relatively stable over time, further emphasizing the interconnectedness of the solar system. The gravitational influences of Neptune and Jupiter, as well as Saturn and even Uranus, help ensure that Pluto's orbit remains undisturbed. While these gravitational forces are subtle, their collective impact cannot be overstated. Their interactions with Pluto and other celestial bodies work together in ways that maintain the structure of the solar system. Without these stabilizing forces, the solar system could experience increased instability, with objects like Pluto potentially being thrown into unpredictable orbits or even ejected from the system entirely.